This is Reigate College Maths, Year 2 Statistics, and the first video on the normal distribution. So the normal distribution models many things in the real world. You've probably seen it. It's often called the bell curve because it's bell-shaped. So it's a distribution which gives us the probabilities of certain values happening. So the probability is given by area under the graph. Now our calculators can find those areas for us, as we'll see a little bit later on. But some key points about the normal distribution is that it is symmetrical. The value of the mean is in the middle. So if this was height, then your mean height would be in the middle there. And the total area under the curve is 1, because the probability that any particular height, for example, is included in our distribution, it has got to be 1 if you take all the heights. Now, you'll see on here that we've got the mean there. This is plus 1 sigma, so that means 1 standard deviation bigger than the mean and 1 standard deviation smaller than the mean give us 68.2% of our population. So for example, if we had heights again, then that would include the heights of 68% of the population. Now those are rules, or those are numbers that you should remember. So within 1 standard deviation either side of the mean is 68% of our population. 2 standard deviations either side of the mean is 95%, 95.4% of our population, and 3 standard deviations either side gives us 99.7% of our population. For all practical purposes, that's really our whole population. So let's go and have a look at some questions which use that. So first of all, number 1, student heights. So here is our height example that I was mentioning earlier on. Student heights are normally distributed, so this is H. So this is how we write this. We write a squiggle, N, that means the heights follow a normal distribution, and then the 2 parameters for the distribution are the mean, and this is the variance. The variance is the standard deviation squared. So what we're going to do is we're going to say, for number 1, let's just write mu equals 1.6, and sigma squared is 0.04, and that means sigma is 0.2. Often we write this like this. We actually write H squiggle N 1.6 0.2 squared. So that would often be the way I would write this rather than putting the 0.004 in there. So let's answer A and B. State the proportion of students that are between 1.4 and 1.8 meters tall. Well, 1.4 is the mean minus the standard deviation, so we can say 1.4 equals mu minus sigma, and 1.8 is equal to mu plus sigma. So what we're talking about is 1 standard deviation below the mean, 1 standard deviation above the mean, and we're going to get our 68% of the population. So 1 SD above and below mean, so approximately 68%, 0.68 probability. Part B, 1.2 is mu minus 2 standard deviations. 2.0 is mu plus 2 standard deviations. So the proportion between those two numbers is about 95%. So we can just do that from these rules of thumb that you need to remember. Okay, let's look at question 2. So question 2 has a number of different parts to it now. So question 2, first of all, it says that we have got, let's bring this up here, there we are, that's better. So we've got our variable x is normally distributed with mean 10 and standard deviation 1.1. So let's just write that out. Mu, the mean, is equal to 10, and sigma, the standard deviation, equals 1.1. You see that we've written 1.1 squared when we wrote out the distribution. That's because it's the variance rather than the standard deviation. So, A, what's the probability that any value of x we have is less than or equal to 10? Well, the probability that it's less than or equal to 10 is the probability that x is less than the mean, and the mean we saw is always in the center of a normal distribution. So you have a probability of 0.5 to the left of it, 0.5 above it. So this is to the left of the mean, so is 0.5. B, the probability that x that was less than or equal to 10. This is less than 10. Because the normal distribution is a continuous distribution, the distribution or the probability is given by the area underneath it. So the probability of equal to any particular number, so equal to 10 for example, that would just be a straight line down. It's got no area, so that's going to be equal to 0. So the probability that x is less than or equal to 10 is the same as the probability that x is less than 10, which is 0.5. For C, we'll see this again, probability that x equals 10. So the probability that any normal distribution is actually equal to a specific number is always going to be 0. It's something that students sometimes find confusing. Now for D, we're going to have to go and look at the calculator. So for D, we need to find the probability that x is less than 9.5. What we're going to do is we're going to go to the menu. Let's find my calculator. There we are. We're going to go to the menu, and then we're going to go into this distribution, number 7. So that's the one with the bell curve, the normal distribution curve, number 7. There we go. We want normal. We want normal CD, cumulative distribution. So that's number 2 here. Now, what we're going to do is we're going to say that the lower bound of what we want is 9.5. Let's draw a little sketch here. There's our, oops, my bell curve not very good there. Our mean is 10 here. We want the probability, everything to the left of 9.5. So this is 9.5. My sketch is too small. So what we're going to do is we're going to put in a lower bound of, well, we could leave it at 0, but I prefer to put in something very, very small here. So let's put minus 100. That's very small in the context of numbers like 10. our upper bound, so we're going to press equals there, our upper bound is going to be 9.5. So we're going to say we're going from minus 100 to 9.5. Effectively, that's the whole tail of our curve here. And then we're going to say sigma is equal to, what was sigma? It was 1.1. And we're going to press equals there. And we're going to say mu is equal to 10. So put in 10 there and press equals. So we've got all our parameters in there, and now if we press equals, it will give us the probability of x is less than or equal to 9.5. So we get that from the calculator. That's 0.3247. 0.3247. If you're asked to give it to a specific level of accuracy, then you should choose 3 significant figures. I tend to choose for probabilities 4 decimal places, so let's leave that like that there. Okay, now let's look at E. The probability that x is greater than 10.5. We see that x is greater than 10.5. Now, because this distribution is symmetrical, we can draw this out and we can say that this is like this. We've got 10 there, we've got 10.5 here, 10.5, and we want that area there. Now that area, because this is 0.5 above the mean and this is 0.5 below the mean, is going to be exactly the same as the probability that x is less than 9.5. So that's just 0.3247 again. And we can see that if we go back to the calculator and we change our lower bound to 10.5 and we change our upper bound to, let's say, 100, so something large in the context of these values for the variable, and press equals, and then we get our 0.3247. Let's look at part F. So F, we want the probability that x is between 9.0 and 9.5, okay. or x is greater than 10.5. Let's draw a little sketch of that. It's really good practice to draw these sketches. You'll find them very helpful. You'll find them that you're much more likely to be accurate if you draw the sketches. So we'll put the mean in at 10. We actually want between 9.5 and 9, so that's that section there, or x is greater than 10.5. We've already found the probability of that, so that there is 0.3247. So we want to find this probability, and then we're going to add it to this probability to get the whole thing. So first of all, let's find the probability that x is greater than 9.0 and less than 9.5. We're going to get that from our calculator. So we're going to change the lower limit this time to 9.0 and the upper limit to 9.5. And we're going to find that probability, press equals there, and we get equals 0.11431. So our probability that we want, so probability that x is greater than 9.0, less than 9.5, or x is greater than 10.5 is 0.1431 plus 0.3247, which is 0.4678. Right, so that is question 2. Let's look at question 3 now, which is a question where we're looking at the mineral water in a bottle. Let's do that on a fresh sheet of paper. So let's put that on here. So we've got the amount of mineral water in a bottle is being modelled using a normal distribution. So find the probability that a bottle contains less than 1 litre of water. So A. I'm not going to write out the this distribution again, but let's just write out what. So before we do part A, let's write out what mu is. Mu is equal to 1.01, and sigma. Well, sigma squared equals 0.01, and that means sigma is equal to 0.1. You need to be quite careful about that. So let's just so A, the probability that W is less than 1.0, we're going to get that from the calculator. So we need to go back to here, and we're going to put in, we'll go up, and we need to put in an upper limit of 1.0. We need to put in a lower limit of, let's put in minus 100 again. To include the whole of that tail, we're going to put in a standard deviation now of 0.1, and we're going to put in a mean of 1.01. And then we're going to press enter, and we get 0.4602. So is equal to 0.4602. Or 0.460 to 3 significant figures, 0.460 to 3. Now the next thing says 10 bottles of water are contained in a Megahack. So what's the probability that all 10 bottles of water in a Megahack contain less than 1 litre of water? Well, for this, we're going to use this probability that an individual bottle of water contains less than a litre. Well, that means that for each one of the bottles, it's this probability, and we're going to multiply those probabilities together. So this is the probability that W is less than 1.0 to the power of 10, because we've got 10 bottles we're interested in, so that's 0.460 to the power of 10, and that comes out to, you're going to need to use your calculator for this. What's a little bit of a shame on these calculators is you can't now do, whilst you're in the probability distribution, you can't do other calculations on here. So you either need a second calculator, or you need to come out and go into its normal calculation mode. So 0.460 to the power of 10, which is 0.0000 0, 4, 2, 6, 2, 3 significant figures. Then the third question here says, what's the probability that at least half of the bottles in a Megahack contain less than 1 litre of water? Well, now what we're going to do is we're going to say in a pack of 10, well, we're going to look at those each of those bottles as an individual possibility in a binomial distribution. So we're going to say that we've got 10 individual events there. They've got identical probabilities, they're independent, so the whole thing satisfies a binomial distribution. So let's call this M is our new distribution, which is binomial. We've got 10, well, it's happening 10 times, and we've got an individual probability of success, so finding that a bottle of water contains less than 1 litre of water of 0.460. We then want the probability that M is, so at least half the bottles contain less than 1 litre of water. So at least half is 5 or more, so we want the probability that M is greater than or equal to 5, which is equal to 1 minus the probability that M is less than or equal to 4. If that's not obvious, then it's worth writing out a little number line here, 3, 4, 5, 6, goes on like that. We want the probability that M is greater than or equal to 5. By number of probabilities we get less than, so we want to exclude less than or equal to 4, so it's the reverse of that, 1 minus the probability that M is less than or equal to 4. So we're going to go to our calculator. If we go option 1, we can select type, we can do binomial cumulative distribution, so that's 1, we can say 2 for variable, so our x we want to be equal to 5, our n we want to be equal to 10, and our probability we want to be 0.460, and then we're going to press equals, and we get a probability of 0.7176. That wasn't what I was expecting. That's because I've put this in wrong. I've put in 5 rather than 4. We wanted 4 here, didn't we? There we go, 0.478. So this is 1 minus 0.478, which is 0.5223 significant figures. Okay, that's it for this introduction to the normal distribution.